现在你还没看出来啊？你还没看出来？这个现在功能先挺漂亮啊，这放这种视频好啊。
你是不是在信息下？对，
那你期待的。
哦。
Okay. The time is up, and today we are very happy to invite Professor Shaposhnikov from the EPFL Switzerland to give us a discussion talk. So for the young student who not very familiar with him, let me make a very brief introduction. Professor Shaposhnikov was born in Russia in the 1956, and he got his degree from the Moscow State University in 1979, and his PhD degree from the Institute for the Nuclear Research of Russian Academy of Science in 1982 for his work on the problem of biosymmetry of the universe in the grand unification theory. Now, he worked from the 1982 until 1986 as a junior research scientist, and from the 1986 till 1991 as a senior research scientist at the CERN division of the Institute for Nuclear Research of Russian Academy of Science. And from the 1991 until 1998, he worked as a staff member of the CERN division of the CERN in Geneva. And in 1998, he was appointed as the professor of theoretical physics at the University of Lausanne. In 1999, he became the director of the Institute of Theoretical Physics of Lausanne University. Now, since October 2003, he was a full professor at EPFL and leading the laboratory for the particle physics and cosmology. Now, his main scientific interest is the relation between the particle physics, quantum field theory, and cosmology. And he works on the problem of the baryon number non-conservation in the early universe and the biosymmetry on the electron wave baryogenesis of the phase transition in gauge theory at high temperature, and the cosmological application of dark matter, and also the cosmological constant and the inflation. Now, he also worked on the alternative to compactification in theories in extra dimension and on the non-topological solidity. Okay, today he will give us this colloquial talk on how many new particles do we need. So let's make a very warm welcome to Professor Shaposhnikov.
Thank you very much. Hello, everybody. I'm very glad to be back to this institute after 10 years, and also observing and noticing how basic science is respected here in China. This is very nice to see that. So what I'm going to do today, I will deliberate on the topic, which is in the title of this talk, how many new particles do we need? Okay. Well, these deliberations, they are based on several works which I was doing with my collaborators. Well, part of these collaborators are written on this slide. Many of them were my postdocs and PhD students at the EPFL. Yeah. Okay, so we can ask many questions about elementary particle physics. So for instance, how many elementary particles exist in nature? Have we found all these particles? How many new particles still remain to be discovered? And of course, all these questions are different questions. So for instance, there could be a lot of new particles in nature, but we will not be able to discover. This may happen because these particles can be very heavy, and if they are very heavy, we won't be able to construct an accelerator to create them. Or if these particles are, well, the example of this type of particles could be, for instance, seesaw neutrinos, if their mass is very large, the order of, say, 10 to the 10 GeV, 10 to the 50 GeV. Also, new particles can be very light, but if they interact very, very weakly, then also we won't be able to create them simply because the probability of their creation is very, very small. So an example here may be an axion with two big coupling, which does not allow us to find them. So how can we find an answer to all these questions? Well, there could be theoretical prejudice. We look at the standard model. It has rather bizarre structure. We don't know from where the structure is coming from. We don't understand why there are 3 generations of fermions and not 4. Okay, experimentally, we know that this is the case, but a priori, we could have said, okay, 2 is enough, or 4 is better. We don't understand why the top quark is much heavier than electron. We don't understand whether the standard model is just a standalone theory, or it is unified with gravity, or maybe all 3 interactions are unified. And this list of questions can be continued. So theoretically, we are not satisfied with that. And then there is, of course, experimental guidance, which can be applied to try to find an answer to these questions. So for instance, we can say, okay, the standard model is a great theory, but there are perhaps few places where the standard model cannot describe reality, so that it is in contradiction with experiments. And that, of course, can provide us a clue to the answer to these questions. Okay, and of course, we may only we can use not only the guidance from particle physics, but from cosmology, put the standard model into the universe. Okay, so there are several proposals to these questions about new particles. So one of them could be that none. We are not going to discover any particles whatsoever. We are not going to find any new interactions whatsoever. And this can very well happen. Okay? It may be that we have discovered everything we could, and troubles of the standard model, which I will discuss a little bit later, are all solved by its unification with gravity. This unification has not been achieved yet, but after all, maybe it's like that, so that we have new physics, new particles at the scale of the order of the Planck scale. But since we cannot make an accelerator with so high energy, we will never find an experiment. Okay, that's perhaps the most pessimistic answer to this question. Well, the next perhaps most optimistic answer to this question that yes, we are going to have 10 to the 32 new particles, and this is the number which was proposed to solve strong CP problem in quantum chromodynamics. Some kind of intermediate answer could be that the number of new particles which we are going to find is roughly the same as we have in the standard model. Okay, and this conjecture is inspired by low energy supersymmetry. So if you have low energy supersymmetry, then basically any particle of the standard model has its supersymmetric partner. And if this is the case, well, then you should discover the same number of scalar quarks, scalar leptons, neutrinos, etc., etc. None of these particles were found, but many physicists were expected to see them at lab and at least. Okay, so what I will be doing from now, I'm going to neglect all theoretical concerns which we have about the standard model and try to use just observations and experiment to see how the standard model should be expanded and what would be the minimal number of particles which would allow us to resolve the problems of the standard model. Okay, so there are just three problems which are solid and which point out to us that the standard model must be extended in some way. So the first one is associated with neutrino physics. So if we take the standard model in its canonical form, as it was invented back in the 60s, then what was done at that time, neutrinos were introduced in such a way that they only have left-handed chiral components. Okay, and why? And if you do so, then you find that neutrinos are absolutely massless. You find that neutrino flavor, number, electron, muon, tau are exactly conserved. Okay. Why it was done so in 60s? Because of this risk. So at that time, it was believed that the lepton number is an exact quantity, and the simplest theoretical way to achieve this goal is to say that we only have that quantity. Okay, so now we know that this is not the case, that neutrinos oscillate, neutrino of electron flavor can go to neutrino with muon flavor and tau, etc., etc. And that tells us that neutrinos have tiny but non-zero masses. Okay, so we should extend the standard model in some way to accommodate that. Yet another problem is associated with unidentified substance, dark matter, and this is where the standard model cracks in cosmology. So if you assume that there are just ordinary neutrinos and dark matter, then none of these particles can explain the missing mass of the universe. There are a lot of evidences for dark matter, but this picture is related to galactic rotational curves, which show that we have more matter than we would expect. Okay? The standard model, again, cannot do the job. And yet another point where the standard model cannot explain reality is associated with the structure of the universe. So our universe contains more matter than antimatter. There is basically no antimatter there. And if you take the standard model, plug it into Big Bang cosmology, then you find out that the number of baryons and antibaryons is the same. And if that were true, all these particles would be annihilated, matter and antimatter, protons, neutrons, antineutrons, at temperatures of $U and V. And then in this picture, the universe would be basically empty, would not contain galaxies, just radiation and nothing else. And this is not the case. Okay. And so this three places where the standard model doesn't describe the reality, and then the difference between standard model description and what we have in experiment is indeed huge. It's not something very, very small. It's really here you expect nothing, but we have galaxies. Here you would expect again nothing, and we see that there is a lot of dark matter in the universe. Okay, so standard model conclusion doesn't explain the composition of the universe. There is another component, that energy, which I'm not going to talk about. Well, in principle, standard model can accommodate that by adding cosmological constant. But say the amount of matter and amount of antimatter, this remains a puzzle. Okay, so how can we try to approach and how we can try to solve this problem? Okay, here is one of the inspiration which might guide us. The first one is Occam-Razell principle. Okay, entities must not be multiplied beyond necessity. So if you have some picture of the world, and if some experiments or experimental evidence is not fitting with our theoretical expectation, we should try to fix that in some way. And let's try to fix that in a way which is minimal, without too much of new stuff. Yet another inspiration which might guide us is related to chemistry. Well, in this particular case, I'm talking about Mendeleev table for chemical elements, who invented some smart table where he put different chemical elements, and then he found that there are some empty spots in this table. In this well, there should be some new elements which we put here, and this was successful. Yet another, so to say, philosophical guiding line may be associated with Isaac Rebbe, who said famously in 36, when muon was discovered, who ordered it? Okay, so this was an unexpected discovery of a new elementary particle, and yeah, why this particle should exist, it was not clear at that time. And so if we introduce some new elementary particles, perhaps we can ask this similar questions. We need this particle because of that and that. And I think that's, well, this is this famous Mendeleev table. Okay, it's not written in this form nowadays. Nowadays is much fancier, much more interesting. Well, anyway, this is from his original paper. There were four empty boxes there for elements, which he called the eco-boron, eco-aluminium, eco-silicon, repeating the name of other elements which were similar to that, and they were discovered. Okay, so this was very profound idea, very profound discovery. So now let's try to do the same. Okay, let's take some table of elementary particles. Let's think that this is table as kind of Mendeleev table, and this is this table, which contains different quarks, well, different other particles, and so that will be a Mendeleev table for elementary particles for us. And this is the situation which we had in particle physics roughly back in 73. So we knew up quark, down quark, strange quark, okay, electron, muon, electron, neutrino, muon, neutrino, and photon, okay, nothing else. And then what was happening in 74, CERN was discovered. And there was a reason for discovering CERN. There were works by theorists saying that you need the fourth particle, CERN, otherwise you get contradiction of the experiment from the properties of different mesons. Then Tau Lepin discovered 75. There was also a theoretical reason for that. If you have three families of fermions in the standard model, then you get CP violation, and you do observe CP violation in K decays. Okay? Bottom quark was found in 77. Also part of third family. Gluon, well, it's difficult to say that gluon was found because that's a particle which is a part of QCD, and the particle is not observed directly. It's not present in finite states, but still this was evidence for QCD. Then Z and W bosons were found, which were also predicted by the standard model. The reason for their existence is the unitarity or stability of the theory. Otherwise, the theory is not consistent at high energies. Top quark, the part of the family, was found in 95. Tau neutrino was directly observed in 2000, also part of the family. And finally, Higgs was found in 2012. Okay, so this philosophy worked very well in the past. It was actually a very impressive historical development. Right now, the standard model is complete with three families of quarks and leptons, gluons, double Z boson, and the Higgs boson. And yeah, it was kind of very impressive also because we were finding in average a new particle every 5 years. Since 73 to 2012. This is the picture which shows a number of new elementary particles which we had as a function of the year. It has pretty strange shape. The number of elementary particles was growing very rapidly up to 1960. Different mesons were discovered. Then it was realized that it's bound states, and so many of these mesons, but most of them were disqualified as being elementary particles. So we went down.
Elementary particle.
Yeah, elementary particle. Not particle in general. Well, otherwise, you nuclei, yeah. So the particle which we believe would be elementary. Okay, and so, but since 2012, we have a plateau. Okay, So already about 13 years passed from this time. And if the previous rate was kept, we should have found 2 or 3 elementary particles since then. But this okay, so if you now say, okay, we use this philosophy, we have a smart table where we put our elementary particles, then this time came to end. Right? You look at Wikipedia, you find out the picture from the standard model, because here there are different boxes. All these boxes are filled. So the conclusion could be no, we don't have, we don't need any new particles at all, because there is no free place in our table. But this picture is wrong. Okay. This picture is wrong, and this is accurate. Okay. We are not going to find it at Wikipedia yet. I'm looking forward when it will be put. So let me explain you what this picture is. So this picture is a little bit more detailed than the previous one. The standard model is constructed in a way that this is a chiral theory. There are left-handed components and there are right-handed components. And in the standard model, if we talk about charged leptons and charged quarks, then they all come in left-handed component, which is the left part of the box here, and right-handed component. So every box is basically split in 2 because you have 2 different parallels. Okay. Now, if you look at neutrinos, then this is not the case. So neutrinos, as we just discussed, they come in just left-handed components. Okay? And so in the standard model, we have on the left, but there could be also right components. Okay. So now let's say, okay, let's imagine that this is the true picture for the standard model. The picture for the standard model, and let's see what is going to happen if we start to fill the boxes. Okay, we fill one of the boxes here. We add one right-handed neutrino. We add one left-handed neutrino, and then you will discover that there is no lepton flavor conservation. Okay, so in this type of theory, there must be neutrino oscillations, and neutrino would have masses, but since we just got one right-handed neutrino, only one neutrino will acquire mass. Okay, and if you do so, you ask yourself who ordered that. Okay, you get an explanation of solar neutrino oscillation. So solar neutrino oscillation, then they require that one of neutrinos is massive. You fill up yet another box. Okay, and then you find that all neutrino physics is explained. 2 neutrinos can have masses in this theory, and we can explain not only solar neutrino oscillations, but atmospheric neutrino oscillations. Okay, and that all neutrino physics can be understood. But not only that, happens that once you have 2 right-handed neutrinos, then CP violating structure of the standard model, well, not on the standard model of this theory, which has two right-handed neutrinos, is very involved and much more rich than that in the standard model. So why we cannot explain baryon asymmetry of the universe in the standard model? But there are basically two obstacles. First obstacle is CP violation. So if you have standard model, we know very well that the only source of CP violation in the standard model is associated with the Kobayashi-Maskawa methods. And moreover, the presence of three generations is essential too. So if you would have just two generations in the standard model, then there is no CP violation. Okay? And this means that in order to have CP violation in the standard model in cosmology, the processes which violate CP in order to make a better asymmetry of the universe should include all generations, all quarks and leptons in the standard model. And this happened to suppress the effects of CP rate. So if you do a computation, you can say, okay, I can get the baryon asymmetry of the universe, but it will be 10 orders of magnitude smaller than the observed. And so that doesn't work. And also, why the standard model doesn't work is because if you take the standard model, then the evolution of the universe to the standard model is extremely small. There is not much happening. Everything is in terms of equilibrium. If you are in terms of equilibrium, then you can get one symmetry. This small suffer of the particle physics explanation. So, if you have a theory with now two right-handed neutrinos, then you have an extra sources of CP violation, which are now in the sector, Latin sector. And in addition to that, these particles, they lead to substantial deviation from thermal equilibrium. So, in this theory, you can now get an explanation why we have more matter than antimatter in the universe. So there is some reason behind. Well, finally, we got one empty box, so we fill it. And we discovered that in this case, that matter in the universe can be explained. Okay. So one of these right-handed particles, it can be long-lived, and we need a long-lived particle to so should I ignore that or okay? Okay. We fill the third box and we get an explanation of another puzzle which we have in the standard model on the dark matter. Okay, so there is even a name of this particles. If you go into particle data group website, they are called heavy neutral leptons, but sometimes the name is changed, but this is all equivalent to Majorana neutrinos, Majorana leptons, still neutrinos, etc. Okay, so let me show you some pictures which can tell us what kind of properties the particles should have. So let's say, okay, we fill these boxes, we can explain different puzzles of the standard model. but at the moment, this is just intellectual exercise, okay? Whether this is true or not, it's a completely open question. And in order to confirm or disprove this picture, you should do some experiment, right? So the legitimate question to ask is the following: what should be the properties of these particles in order to do the job? So in particular, we want to explain all experiments in neutrino physics, and we want to understand what is the why the universe contains more baryons than antibaryons. Okay, so the computation which can be done, which has been done, is the following. We take a theory. The first condition is that it should get correct neutrino physics, so that neutrino mass differences, neutrino mixing angles. So that's the first requirement. And the second requirement is that the theory should produce correct baryon asymmetry of the universe. So the number, when I talk about baryon asymmetry of the universe, I'm talking about explanation of the baryon to photon ratio. We take the density of baryons in the universe and we divide it by the density of photons. Okay, so this number is of the order of 10 to the minus 10. About 400 photons in cubic centimeter have around 1 nucleon per cubic meter, and that makes us this number of order of 10 to the minus 10. Okay, so and this is the picture which shows when both conditions can be satisfied. So remember, baryon asymmetry of the universe and neutrino masses were explained by two heavy neutral leptons. Okay, so here is the mass of these guys. It's just one number because it happens that for explanation of baryon asymmetry of the universe, the masses of this sheet particles should be close to each other within 3%. And so there is just one number on the horizontal axis, and the vertical mixing angle, as traditionally called in neutrino physics, and a mixing angle. Okay, so what this mixing angle is telling you, it's telling you how to compare the strength interaction of this new particles in comparison with the strength interaction of ordinary nuclei, which are associated with number. This number here is smaller than 1. It shows that this interaction is much weaker than the liquid interaction. Several orders. And then you get this picture here. So this region is ruled out because if you are in this region, you cannot accommodate neutrino physics. The neutrino masses happen to be small. If you are above this number, then you cannot produce matter-antimatter asymmetry. So the reason here is that this mixing angle is too large, and that leads to equilibration of these new particles with the uniform equilibrium. You cannot get variables. So this part out, this part out, and everywhere in this white domain, you can get baryon asymmetry of the universe and whole neutrino physics right simultaneously. Well, on one hand side, this picture is very optimistic in the sense that if you read, it will be detected by the future climate. Yes, I will. I will come in a second. Yeah, so as I said, on one hand side, this is an optimistic picture. Okay, you say, okay, you take this theory, and then there is a pretty big parameter space where the theory is relatively fine. It can explain puzzles of the standard model. Also, this figure can be considered as pessimistic because there is no end here. This wide domain.
Rectangular neutrino mass is a kind of underestimate. So you already showed that it's far to the right. Yes.
Yeah. So basically, the mass of CSO you cannot be fixed by neutrino. You know that there is Geneva associated with the power cup. So you can take the mass very large, the power cup larger, or we can make the mass of CSO neutrinos smaller, smaller the power couplings. It doesn't matter. Neutrino physics and neutrino oscillation experiments, they don't measure. The experiment which would measure absolute value of neutrino masses are also consumed, are also suffer from this change. So whatever okay, this is all about the scale.
Is there any function if you want to use that to explain dark matter?
Okay. Okay, so it may be very well that the mass is 10 to the 15 GeV, everything works. Neutrino physics works, there in the symmetry exists.
So here, mixing that it comes from the dark mass.
Yeah.
And then in this case, for the how about the mass
well, the CSO formula is and yeah, it's right. It's Liparo square. This Dirac mass square divided by rho. Right? And you will be in the model, so you will be in physics. Down to my random mass of the order of 1 electron volt. Okay. From 1 electron volt to 10 to the 15 GeV, everything. But unless you see both neutrinos, there are experiments, there's indeed experiments and many others, many other discrepancies, which are associated with the short based on neutrino experiment, where people say that the dust hasn't settled yet in this experiment. They can be each other, and the picture is not easy to accommodate this type of cosmology, scenario that leads to the unification, asks etc., etc. So, if the picture which I'm telling you about is right, then all this low energy discrepancies between physics are the part of that. If the picture finally is for neutrino will be found in one correct from the gene, then the picture in the mouse will be useful.
So,
perhaps I will do something about that in the next yeah, so just to finish with this slide, there are other lines here. So there is green light, and this is the part which will be accessible by experiment at CERN, which was included last year, which is called SHIP, Search for Hidden Particles. Then this part is, okay, it's put FCCE, but there is a very similar part associated with CEPC, very similar. CEPC at the moment is just a little bit higher than stereo, and that would be a great experiment that enough having P plus and minus collisions at ZO, and then there is some part that can be done in the hybrid. So if the particles happen to be in the domain, then the theory start to be testable. Okay, now I'm coming to that matter and also to the question. So there is a third neutrino there, which may play a role of the dark matter. Okay, and there are several constraints on the properties of this neutrino, which are also shown at the similar plot. So this is the axis where I put the mass of this particle, and this is again the mixing angle. So the sense of the mixing angle is exactly the same as for previous particles. But here, notice that the energy scale is different. This particle, it's better to be light in comparison with others. So for others, the scale was GeV, or hundreds of GeV here, but here the scale is KeV. Okay, you can understand very easily why the scale of the mass should be very small, because the particle is not stable. So it mixes with ordinary neutrino, and through the mixing, it can decay in really thin. And as every with decay, the decay rate is proportional to the mass of the particle to power 5. The muon, whatever. So the larger the mass is, the shorter its lifetime, but the lifetime should be greater than the lifetime of the universe. Otherwise, this can be a button. And so that tells you that the mass should get to be small, and also the mixing angle, which also suppresses the dip, that should get to be small. Okay. Then there are two, well, I better to say three very stringent constraints on this candidate dark matter particle. So there is this line, which is theoretical. You take a theory, you fix the mixing angle, and then you compute the abundance of this particle, because they can be created in neutrino interactions. Okay. The process neutrino gives you this particle plus another neutrino. And if the mixing angle is larger than this line, you get overproduction. You have too much of dark matter. Not good. Then there is yet another limit, very stringent, which says that the mass cannot be smaller than roughly half of KeV. Again, this constraint is the famous German-Gunn constraint. Any type of Fermi construct dwarf galaxy, you have to put enough dark matter inside this galaxy, and since this is Fermi, you can put more than one state. That leads to a lower bound and the mass of this particle, which is very robust, which is about 0.5 keV. Okay. Then there are experimental constraints, which are coming from X-ray observations. So from where it's coming from, the particle can decay into gamma, one and another neutrino, really good correction. And since this is a two-body decay, then the photon which is emitted after this decay is monochromatic. Okay, so there is a quote redshift associated with the universe expansion where you define this particle in the universe, but this is a monochromatic line. Okay? And you can search for this line. It is in the TE region here that makes interpretation of the searches ambiguous because there are other lines there which are associated with chronic transition, but still we can put also stringent constraint telling that okay, this is excluded. There is some suspicion point here. So some people claim that new line was discovered, 3.5 kV line. If this line is there, then it may indicate that magnetic particle 0 kilograms, this is the mass 7 kV, but still the evidence of this interpretation and this experimental data is far from being overwhelming. So maybe it is there, maybe not. This considerations, they lead to prediction of the absolute scale of neutrino in this field. So why is that? So because in CSO formula, potentially 3 right-handed neutrinos are visible. Okay? But if one of them is dark matter, then you can estimate what is the contribution coming from that matter neutrino to the mass effective. And then we find that this mixing angle is so small that there is no such contribution. It is extremely small. Okay? So this means that from the point of view of neutrino physics, we just have 2 mass liquids. Okay? This means that the lightest of active neutrinos is practically massless. Okay? And that tells you where you are in, so basically the minimum neutrino mass should be smaller than the minus 5 electron volt, and that tells you where you are in this plot, which is plot of neutrino that's you are in this not here, but we facilitate discovery of another neutrino mass. That happened to be okay, and since the theory is really very, very minimal, then there are a lot of exciting connections with the neutrino physics. Okay, so you can take the Lagrangian for this model with the right-hand neutrinos, count the number of unknown parameters, count the number of known parameters, and then make predictions. So for instance, if, so that makes the model testable. So for instance, let's take this graph. So what this graph shows, it shows the coupling of new particles to electron neutrino, to tau neutrino, and to muon neutrino. Okay. Now, if these particles are discovered at some experiment, then this discovery will allow us to find this different flavor couplings. Okay, and then from the analysis of the current neutrino data, we can predict what are the allowed values. So that would be allowed values for inverted order, and that would be allowed values for normal order. Okay, so you find these new particles, you say, I found a point here, theory is rejected, doesn't work. Now, if you find something here, then the theory is the open importance of observational data. Okay, perhaps I should make a remark here that we don't have really much data at hand which allows us to pin down what is the correct theory. We just have well, a few numbers from neutrino physics, baryon asymmetry of the universe, dark matter, abundance, nothing else. And then the number of these numbers where the standard model doesn't fit the experiment is not huge, it's small, then it's clear that one can invent many different theories with the similar predictions. Okay, so one of the example is evoked by David Glass, Futoshi Maruyama, and others, which said, okay, if we have two new particles, scalar field, the real scalar field, which plays a role of dark matter, two very neutral leptons, very heavy, then one scalar with mass to drive inflation, then it can also do the job. The trouble, say with this theory, well, it's not a trouble, it's unfortunately, it cannot be experimentally tested because there are particles which you can discover. Okay, so suppose this is all right. We can ask the question, how much time it will find necessary to find this new particle. Well, it's not easy to answer these questions. We can look in the past, look at different developments of the standard model. Okay, the standard model was first invented about works at all, leptons. And then it was the part of the standard model in the sonic sector was staying intact during all the years. It was happening that theoretically the number of quarks and leptons was growing. Well, basically it took 20 years to find quarks and leptons of third generations and 50 years to confirm the standard model. Well, here I want to be a little bit more optimistic. So dark matter perhaps can be found at CRISM. So CRISM is a satellite which was launched in Japan in 23. It was supposed to search for narrow lines here. So in particular, the line which may come from CERN neutrino, but there are no physics results yet. Perhaps they have some technical problems. And two other, perhaps they can be found at ship at CERN in 31, okay, probably later, or at FCC or CEPC later if these accelerators will be constructed, which I hope very much will be the case. Well, this just a slide shows what this CRISM does. It's an X-ray spectrometer, which has very good energy resolution. And this is very important to have very good energy resolution because then you can measure the gamma quanta, or X-ray, at very high precision, and that will allow you to distinguish this line from other lines which may happen in atomic transitions. Okay? So that would be a great thing to have results from them. So what is experiment at CERN? Shift, as I said, search for, oops. Yeah, search for hidden particles. So this experiment was proposed back in 2012. The first method written at that time. Then it found selected at CERN and SPS in North area last year. So the great thing about this experiment is that the sensitivity of it is 10,000 better than in all previous experiments in this energy domain. So you are opening a huge part of the possibilities. And let me just explain how it works. It's very simple. So there is SPS accelerator at CERN, which was used to discover W boson, for instance, right, and which has the high intensity proton beam with energy 400 GeV. Okay. Then imagine that this beam is entering here into the target, so it hits the target, and when it hits the target, it produces different type of masons. It produces K masons, I masons, the stuff, and so it produces, for instance, D, and then D can decay into muon and muon neutrino. Muon neutrino mixes with the HNL, and so in this way, very shortly, because D has a short lifetime, so somewhere here, you create the new particle. Okay, so that's that happens here. Then there is a part of this instrument, which is very important for experiment, which swipes away new mesons which appear after the beam dump. Okay, so you produce a lot of mesons, pi mesons, whatever. They decay, produce new mesons, and new mesons you don't want to see because they give the background. So there is an active muon shield here, which sends this huge amount of mesons out of your detector. Then there is a decay volume here, okay, where this new particle can decay. And so it decays, for instance, on pi and mu, and then you can find the spectrometer the decay products. Again, by analyzing these decay products, we can figure out whether you got a decay of new particle there. Okay, there are other different proposals to search for similar processes, plenty of different experiments here. Also, well, what I told you here would work only if the mass of these particles is smaller than the meson. So the largest mass of the meson which we can get is beauty. So it just works up to 5 GeV. Now, if the mass is larger than 5 GeV, then we need something else, and then we can use Z. We can produce Z in plus or minus collisions, and then we can search for processes in which Z decays into neutrino and HNL, and again we can search for decay products. And the best accelerators to do so would be FCC and CEPC running in Z mode. Okay, so this is a busy plot showing what we can reach. This is the mass, this is the mixing angle. So this line, we better get below this line because it is in this region we can explain baryon symmetry and neutrino physics at the same time. And then this is the curve for ship. And then there are other experiments such as Matusla, which was proposed to be at CERN. So FCC, well, and CEPC will be here as well. So actually, if you increase the luminosity, you can even touch the seesaw line, and this is shown in new plots. It's a little bit outdated. And you can search also for other type of weakly interacting particles in this experiment, in shape, and CEPC, and FCC, such as dark scalars, dark photons, dark Higgses, etc., which are actively discussed now. Okay, so I'm coming to my conclusion. How many new particles we need in particle physics? Well, we have just 3. Okay, so these are heavy neutral electrons, which can be the key to all experimental problems of the standard model. Neutrino masses and oscillations, baryon symmetry of the universe, and dark matter. Just a side remark is that we also would like to understand why the universe is flat homogeneous and isotropic. So we need inflation. This can be Higgs boson can do the job. And so I'm optimistic. Hopefully, we will be soon in an exciting point in history. New experiments at the intensity frontier, such as SHIP, CEPC, FCC, and chances to discover particles responsible for neutrino masses and baryogenesis, and X-ray experiments in space discovered the origin of dark matter. Thank you very much for that attention.
Just the standard neutrino
Now, this is, well, yet another explanation which also would fit in this minimal health picture with related to maximum, which I didn't mention here. And I didn't mention this problem at all in my talk. This was not because against or something, simply because of not
so neutrino reference.
yeah, so
big issues.
We have the next step, maybe for.
I have another question. At the beginning, you mentioned that to solve the CP problems, you need the up to 32 new particles. How to get this now?
Well, this number, well, it's not my work. Yes, that was the work by Biography and grams per hour. And they said that if you have this is
it's a bigger number.
Yeah, that's a big number. This number is basically derived as follows. You take the Planck mass, you divide it by the electronic scale, you get about 10 to the 6 scale, and then there is scale. So there was some argument associated with the entropy for black holes, and so you have to
so something like the landscape, from the slit and then here. 10 up to the bigger number of vacuums.
Yes. But so the first I cannot reproduce the arguments. But this number is in the abstract.
Okay. Okay.
Are you considering to run it?
Yeah, well, it's all my running. Yeah. So the logic here is we fill these boxes. Okay, we put 3 right-handed nuclei. Okay, one the theoretical point of view. These particles are singulars with respect to the standard model group. Okay. And since they are singlets, with respect to this group, we ask ourselves what is the most general interaction which we can write, what is the most general Lagrangian which we can write, which respects the standard medicine. Okay. Then the Majorana mass terms are allowed for this part. Okay. And so I would say that they should be there. And, so how can that Majorana mass? Now, there is, of course, theoretical possibility to say, well, maybe there is global symmetry. Well, in the standard model, there is a global symmetry, which is the baryon number minus vector number. Okay. So, if you say, I want to respect this symmetry, okay, then you cannot add Majorana neutrino masses to the theory. From the point of view of neutrino physics, this theory is perfectly fine. Okay, it can explain all neutrinos oscillations, no problem. The disadvantage of this theory, from my point of view, in the linear picture, is that this theory cannot do barogenesis. It doesn't have a neutrino, it doesn't have pragmatic entity. It could be the case, but then you should say, well, if the theory is not complete, there is something else which gives me that method, for instance, that's CERN, no problem. And it should be barogenesis. But to get barogenesis, then we need more rich, so to say, extension.
On symmetry on the increasing kind of fields. If we take the left hand and right hand symmetry family physics, then if you want to have the neutrino another one, then you need to reproduce the check backward and check backward and right hand check. It's divided not enough the neutrino. Yes, then you will be enlarged and you produce more particles. Also, in that case, we can also see there can be primitives on like symmetry. Yeah, but if we understand the question correctly, really that's when you can tell me if this is answer to your question or this is answer to something. Okay, so here in this approach, the word minimality plays an important role. Okay. So if I have right-handed neutrinos, they are very much different from left-handed neutrinos, not only because of their chirality, but also because of their quantum numbers. Because left-handed neutrinos are in doublets, and these guys are singlets. Yeah, because if you use singlet, you can construct the arbitrary, like easy. Actually, if you type a left hand and right hand, the travel symmetrical. Yes. It's symmetrical. You also have the right hand doublet. Yeah. If you want to construct the model, of course, this type of models were constructed a long time in the past, because there was a puzzle why the standard model is spiral, why they have left-handed stuff, not right-handed stuff. And of course, one of the proposals was that left-handed part and right-handed part should be very much similar. The standard model group should be not just SU2 left cross U1, but SU2 left cross SU2 right, and then the right-handed doublets, etc. And then the difference between left-handed and right-handed comes because of spontaneous symmetry breaking between left and right. So this is, of course, very nice idea. Many people studied that. It's fine, absolutely fine theory. It's more complex than this one to contain part. But it can only build a similar type. you can always contract the low energies with this field.
Yeah, yeah. So if you say, okay, I like left-right symmetry, as Goran Siljanovich told me immediately. Then we have to satisfy experimental constraints. Right? And then we have to say that the mass of right hand that's W boson should be much larger than the mass of this.
Let's go to see in the figure. Those we want the right-hand neutrino not having the left-hand neutrino. And you'll see, so for example,
Yeah.
you have so small with the mixed angle.
Yeah.
Then the question is how is it on tuning, or is the symmetry protected, or is due to oscillations?
What the parameters here are not predicted.
Yeah, that's right.
As well as the parameters of the standard model, we are taking them on itself. Of course, this is a big disadvantage of our present understanding. We have this low energy series, we can't predict anything, we just taking that from experiment. So the question is, like, why this mixing angles tend to be expand are not answered. As well as the question why electron is lighter than the photon. We need some belief embracing theory which should tell us what is it. It would be great if we did.
Well, maybe just for your further comments for this global symmetry. Yeah, from my some point of view, all the symmetries of basically like to have to the doctor symmetry, global symmetry.
Yes, so well, okay. So this global symmetry B minus L is in any way is an accident symmetry of the symmetry. Okay, so for instance, if you say I take the standard model and add all high dimensional operators which respect the gauge symmetry, then of course you're going to break B minus L.
Yeah, if you have SU to add, SU to one, and SU force then you have automatically like that symmetry.
Yeah, in this case it will be good symmetry. Yeah, you can also get yeah, you can also yeah, but I agree with that. We don't have global symmetries well, even if we have to have the gravity presumably breaks or global symmetry or as you say, maybe it's the
okay, then another place for problem. The problem is for local symmetries actually for the coordinate system. Uniform quantum field that parts. The equation actually is, as we said, is limitation. All standard model and quantum field. We take the spacing B right hand part as global symmetry. We take the symmetry of this quantum field. That's maybe it's also the limitation, but we don't understand about the space symmetry. Would also be opposite.
I do agree with that. Moreover, I gave a talk at CBS meeting, actually as a deliberating this talk. So my point of view is exactly the same. So I would say that global local symmetry is kind of strange. It's present to local global symmetry, and if you do so, then you get black.
That's right. That's my contrast over edit calculus.
But yeah, so that's completely sure this very simple integration,
More in the lower symmetries, in order for coordinate, you have to separate the local symmetry of coordinate and the space symmetry also. I identify to the space symmetries. That should be log part. They are different.
I have when first applied the last point about the principles. It means that principles to as the infinite. But as far as there should be non-minimum cut. This also is how much. Do you have any explanation about the non-minimum?
Well, the only explanation which they have is the following. Okay, so suppose that we write the standard model and then we have Einstein field reflection. So we consider minimal coupling of all the fields. Yes, right. That's fine in theory, but then let's look at randomization of this field. And well, the whole right? Yeah. So basically, the non-minimal coupling is certainly there because of the following reason. We don't know how to compare gravity. Let's take the ground field and the ground method, which is material. Still, electric theory should be normalizable there. Then you look at the diagrams and you do see that the term this minimal coupling is generated. So not only that, we see that this minimal coupling is generated, that the corresponding diagram is this minimal coupling and they approach. And if you stick to the standard rules of the normalizable field theory, once you see something which is divergent, then you should introduce that. First point, and secondly, we don't know what it is. So it can be looked at. It is measured from its value. And so you can say, this minimal coupling should be 1 side. And then inflation.
Yes. Okay. Due to the non-minimum coupling, then the coupling principle is correct.
No. Why not? Not because of the following. Because the equivalence principle is associated with deep infrared part of graph. So it's associated with something massive. This is a gravity state. And this non-minimal coupling, it introduces you just the coupling gravity with the fixed field, which is massive. And that's it. But it basically tells that there is no violation of so there is no
pretty the vacuum of the big person is so small. It's not enough to produce a promoted potential. I mean, drive the effects.
No, of course not. Well, no, it is not. No, it is not in the fixed field as well. So what
because the quantum factor or the original potential?
No, well, it works in the following way. So like we have discussed, this unique minimal coupling. The master introduced it, and they don't know what the value of this minimal. So once it is introduced, the coupling of the gravitational part of the theory is Einstein field term plus its square times r. So now you ask yourself what happens in the theory when the Higgs value is very, very light. By very, very light, I mean that the contribution to this coefficient in front of our term coming from the Higgs is larger than the Planck scale. Okay. And then you see that
dynamic.
Yeah. So it's the idea here is resembles that of chaotic, where you say, okay, I have some potential for the fixed field, and then my initial conditions for initial field are not necessarily at zero, but somewhere else. And then with the regions where the scalar field is sufficiently large, they inflate. Those where fixed field is small, they don't. And they don't care about them. They live in the part. And this perfectly fits to this. Whenever you take the fixed field, which is larger,
Practical
Yeah.
radius is large.
yeah. And then this energy is perfectly enough to inflate with.
In some sense, it's like a factor of technical constant.
Yes. Yeah, precisely. Yeah, so this is very important because if you have a big field which is large,
Yeah.
you can neglect Einstein Hilbert theorem.
Yeah.
You get the Newton constant for the Planck scale, which is determined by the fixed field. So all dimensional full parameters in the standard model, the masses of all particles are all proportional to the fixed, and the Newton's constant Planck mass is proportional to the fixed, and that basically means that nothing depends on the fixed.
Why you prefer the Higgs boson is not for additional skeletons.
Yes.
It's going to be additional skeletons on top.
Yeah, okay.
Skeleton.
Yeah.
It's interesting. Huh? So people used to talk about the slash model. It's not that model for epsilon for six was Higgs model as Higgs model to the the only difference in this picture is that we only is epsilon. So why we only epsilon?
Right, I simply didn't talk about that here for the sake of
To see that.
simplicity, because I found it important. Mistake on PS minimal extension involved in the beginning of life insists that in wild invariant Einstein are undressed. So we could say wild invariant Einstein will come. Right? When you reproduce everything which I said here, once you get maximum in relation to the needs. And then you find you don't take the problem in addition to the yeah. So I really thought that it was simply
otherwise not going to see it in class. You see the top mass, the 3 sigma below beyond
the second question, there was a question about the stability of the electronegative, so to say. Yeah, so the short answer is that if the top mass is smaller than some critical value, okay, then the scalar self-coupling, running of the scalar self-coupling in the standard model tells you that it is always positive. Okay, and then everything which I said, it goes through. It may happen that the mass of top quark is larger and so that the scale is set up once, and to get some negative value at some state. Okay. In this case, Higgs inflation may not work, or may work, and that depends on known unique inflation in the field. If there are unique inflation in which the negative value of the scale coupling feels Higgs inflation, but there is another domain in which it's still faithful. I can elaborate with that if I have level.
About we can have
It's a screen.
That's that. Corner in the corner, maybe you put onto that corner
from the side.
Yeah.
Let's see. And there is a chalk somewhere.
I understand your solution. Actually, the current solution is what is the finishing problem. In one direction, we have nominal quantity. In another direction, we have R-squared gravity. And the final picture is that is not the Higgs because combine the direction in the
This is also a possibility. So we was talking about let's say modified gravity, which contains not only R term but R squared term. And then in R squared term, and there is an extra particle in this theory, which is basically Starobinsky inflation. The universe can be inflated. This is also a possibility. It has one extra particle. No. In Higgs inflation, there are predictions. There is also scale which is also very much similar to laboratory if you take the matrix, which is ACT measurement, which means that the scale with 5 factors, and there depends the Higgs inflation in the matrix. It's measurement of the value of Maybe other platform.
Those are facing
Okay, you make it much like
so it doesn't know speaker there.
Thank you.
好像不行，它只是左边一块右边一块一样大。